We can generalize this to a way to split a sum into several. I will not give examples this time. I will barely state the rules because you can see it all in the notes, including examples. So let's state this. Let's state the version of this fact for several subsets. Let S be a finite set. Assume that S is decomposed into n disjoint subsets, S1, S2, and so on as n. And again, disjoint means pairwise disjoint, so Si intersects Sj in the empty set for all I not equal to j, and decomposed means that S is the union of them all. Then the sum over the whole set S is the sum over the first subset plus the sum of this over the second subset plus the sum over the third and so on plus the sum over the last. And you can restate this using the summation sign once again. Namely, it will be sum over I equals 1 to n S in Si As. This is what's called a double sum or a nested sum. It's a sum and its addends themselves are sums. Don't be surprised, these things appear in nature very often. So it's a sort of divide and conquer technique when you're using this theorem. You're splitting up the sum into many little bunches and you're adding each bunch separately and then you're summing the totals. A very closely related theorem, really just another way of stating this one, is the following. Let S be a finite set, let W be a finite set. Let F from S to W be any map. Not bijective, not surjective, whatever. Of course, it can be. Let AS be a number for each S. Then sum of AS equals sum over W. And I will explain this in a moment. So on the left, I'm just summing together all of the AS's. On the right, I subdivide the sum into bunches according to the value of f of s. For each possible value that f of s can take, so for each possible w in w, I sum all the as's with f of s being that value. And then once I have all these totals, I sum them all together. So for example, I will not show you how this is proved, but this is in the notes if you want to read it up. Let n be a positive integer, let m and n. Proves that sum of the remainders modulo, from k equals 0 to mn minus 1 of k remainder n is mn n minus 1 equal over 2. Why? So the trick here is that these remainders repeat after n numbers. 0, 1, 2, and so on, n minus 1, 0, 1, 2, and so on, n minus 1, and so on. So the easiest way to compute the sum is you split it according to the value of this remainder. So f sends each k to this remainder. That's the best way to split the sum.